Oh, what? Okay.
Okay, so here we go. So welcome everyone. This is the Easter edition of MOPA, and I'm really very grateful to Paola, who has agreed to talk to us, and Paola D'Aquino from Naples. She will talk to us about residue rings of models of Peano arithmetic. Welcome, Paola.
Okay, thank you, Roman, for the invitation, and sorry for all the problems before, but I don't know how to do it. Sharing on Zoom. So this is a joint work with Angus McIntyre, which is still going on. We have some partial results, and I will try to explain them. Okay, so the goal is the following. If we have take a model M of Peano arithmetic and an element in M, what can we say about the model theory of these rings? There are some previous results which go back to 82 when for n a prime, and this is due to Angus. And what we have examined is the case for n a power of a prime. So where p is a prime and k is greater than 1. And then it's still a work in progress when for any n, so what we call n composite. And the analysis uses valuation theory. Only that is the main tool. So I recall a few basic things that I will need. This is a list with not the, I don't pretend to be to say everything which is needed, but the majority. So for what happens for Z, the standard model of Peano arithmetic, actually here I have to say that I will tell also later, but I mean, I don't make any distinction between the model of PA and the ring associated to it. For me, M is both, denotes both. I don't make any difference. So in case M is the standard model, we have that the quotient Z over P to the KZ is an Henselian local ring, and the maximal ideal is Z over P to PZ. And both of these properties are first order expressible, definable in the language of rings. What is this is a known fact that this quotient ring is isomorphic to the quotient of the p-adix with the corresponding element. So where pz is the ring of p-adic integers. And for what is needed in many of in some of the arguments is also that there is, for each fixed prime P, there is an existential definition of ZP in QP, where QP is the field of p-adic numbers.
May I ask a quick question, please?
Yeah.
Yeah. Which numbers are standard and which can be non-standard?
No, we are working in MZ, so these are, everything is standard.
Ah. Thank you.
I'm just reviewing what is known for the case of Z.
Mm-hmm.
Then I will switch to the case any M no standard.
Mm-hmm.
So for a fixed prime, then of course this is the ring, the theory of Z over P to the KZ is decidable, is a finite ring, so we know everything. And also the theory of all Z over P to the KZ, as P, the prime P varies and K varies, this is decidable, and this is due to X, as the last three statements that I wrote. So for each finite, this is trivial. The second one, the theory of all the Z over P to the KZ, and also the existential theory of the ring Z over MZ. This is decidable. These are all in the paper of X on the elementary theory of finite fields, going from 68. And he leaves it open in the last page if the theory of all z over the mz is decidable. They prove as a consequence of his result that the existential theory is decidable, and he leaves it open if the theory of z over mz as m varies is decidable. Okay. So yes, this is this is left open, and then there is a result due to Dirac-Chan and McIntyre, which is unpublished, that they prove the decidability of the theory of all the z over mz, and they use they prove it by reducing to the ring of finite adels, where they have the result of the decidability of the ring of the finite adels, and so they interpret the theory of z over mz in this ring of finite adels, and so they get the decidability result. For finite rings, there are also negative results. These are classical, that the elementary theory of finite commutative rings is undecidable. This is an older result of Rabin from '65. And from this, it can be showed that the elementary theory of finite local commutative rings is undecidable. Okay, now I switch to consider M non-standard. So I work in the language of arithmetic with the usual plus and times 0, 1, and order. And as I said before, I won't make any distinction between the positive part, which satisfies induction for all definable subsets, and the ring associated to it. In these rings, any element we call it a non-standard prime if it is greater than all the standard parts, and if it satisfies the following first order property, that for all y and z, if x divides the product of y, z, then it has to divide one of the two. It is well known that for this in M, in any model of Peano arithmetic, but even much lower down, that every reducible element is prime. So the equivalence between irreducible and prime. That every definable principal ideal is principal, and any principal prime ideal is maximal. If it's not principal, then it's not necessarily prime equal maximal. So also in the treatment of the case when M is not standard, I will distinguish the three cases that I have examined, I mentioned before for Z. So the first case is when N is a prime. Then we have that N is a power of prime. And this power of prime may be either standard, non-standard. I will make some distinction, but in general, we have results for general P and K. And N composite. So what this means to write P to the K, this has a very well-known meaning in any model of Peano arithmetic, because we know that there is a formula which defines the graph of exponentiation in any model of PA. And so the expression P to the K as an unambiguous meaning identifies uniquely the element which is P to the K.
May I ask a question about actually it's about the previous slide, because your definition of prime was not the usual definition of prime.
Well, yes.
Does it matter? Is it?
No, because it's
doesn't matter.
It's the same. Yes.
It's the same. Okay.
reducible, this is reducible and prime is the same. Yes, yes, it's the same. It's equivalent.
Thank you.
So this is not the case for very weak arithmetic like open induction, but for this induction is more than enough to prove this, the equivalence.
Great, thanks.
Yeah. So Axe also in the paper that I referred to before, he determines axioms for K, a non-principal ultra product of finite fields, and this is a perfect field. It has exactly a unique extension of each degree n, and then it is what is called PAC, i.e. every absolutely reducible curve has a K rational point. And the fields satisfying these axioms are called pseudo-finite fields. If the characteristic of K is 0, then K is elementarily equivalent to a non-principal ultra product of prime finite fields. So the result of McIntyre 82 is the following. So you start with the M no standard, and if you take a P, a prime, then you distinguish, there is, if P, the first case, if P is a standard prime, then trivially the quotient field is isomorphic to the field with P elements. And if P is non-standard, then the quotient field satisfies the axiom of Axe. So the quotient is a characteristic zero field. It has for each extension, it has a unique extension of each degree n. You have just to formalize in PA the classical argument, and PA is able to do that. There is enough induction for, is quite powerful, has power enough to reproduce the whole argument, the formalization of all argument. And then M is, the quotient is a PAC. Not in the form that I said before, but in the following form that, because this other form the formalization is due to Bombieri of Wales-Riemann hypothesis for curves over finite fields. So this one can be formalized in PA, that if C is an absolutely reducible curve of genus G, defined over FQ, and then is the number of points of C in the finite field with Q to the M elements, then there is this bound. So this is just to show, it's not important to understand all of it, but just that this formalized version, this version can be formalized, and there is one for each natural number. N is a fixed number. So the genus is the genus before they have to run over natural numbers. It's not that we go to genus of the genus here is a genuine natural number. Okay. So in this case, then we can say that the quotient field, because this is a field, is elementary equivalent to an ultra product of prime field from Axe result. In this case, Q is a prime. And of course, then D is a non-principal ultra filter on the set of primes. I'm assuming that I'm considering the case where P is not standard. These fields are all recursively saturated, both if P is standard and non-standard, essentially because we have a satisfaction class, satisfaction relation, because we can bound all elements by this P. So the bounded satisfaction classes which exist in PA working in this in the residue field give a recursive saturation. And also, if P is non-standard, this field is not a recursive field. So what is normally called in the modern theory of Peano arithmetic, that this is subject to the Tenenbaum phenomenon. The usual, you can reproduce the same argument that for PA. So what it shows is the following, that for every pseudo-finite field of, so a field which satisfies the axiom of X, there is a non-standard model M and a maximal ideal such that K is elementarily equivalent to the quotient of M over I. So this M is constructed via ultra products of Z. Because if K is an ultra product of finite fields, then you take the finite fields as Z over P QZ, if you go back to the previous slide. Okay. So if, yes, here, so the finite fields is like this, and so we have that FQ is Z over QZ, and so the ultra product is functorial, and you get that you get the existence of this non-standard model of PA, which gives in the following slides, yes, the elementary equivalence of M over I and K. And moreover, he showed that for every pseudo-finite field I, for any pseudo-finite field K and every non-standard M, there is a maximal principal ideal I such that M over I is elementarily equivalent to K. And then you can actually show refining using also some work of Cherlin that there is also a non-principal maximal ideal, which is elementarily equivalent to a quotient by a maximal principal ideal. So for countable pseudo-finite fields, we have the following, that, one thing, this elementary, the elementary in 2, in the second statement, the elementary equivalence cannot be replaced by isomorphism unless, because as I said, these quotients are all recursively saturated, while K not necessarily is recursively saturated, and so isomorphism usually doesn't hold. But this is, let's say, that is the only obstruction. In fact, indeed for kappa, for K, a countable pseudo-finite field, the two A and B are equivalent. So K is recursively saturated if and only if there exists a model M and a prime such that the quotient of M over PM is isomorphic to K. Okay, now we move to higher power of P. So still in the context of M no standard. So I take the p-adic valuation. I recall the p-adic valuation. This can be defined also in any non-standard model of PA. Like I fix a prime P, and V, and for any A in M, Vp of A is the highest exponent H, such that P to the H divides A and P to the H plus 1 does not divide A. And this valuation induces, in a natural way, a valuation which we call a truncated valuation on the residue ring. And the values are taken in the initial segment 0k. So the ring, this ring M over P to the K M, the principal ideals are in correspondence, are linearly ordered by divisibility and are and there is the minimum one, which is with K equal, which correspond to 0, the prime ideal, and the maximum, which is P. So what I mean is the maximal ideal is PM over P to the Km. So these are all linearly ordered, the principal ideals. And they are reverse ordering with the exponent. So from this, we can prove basic algebraic properties that the quotient ring M over P to the Km is an Euclidean local ring. So it is Euclidean and local, it has unique maximal ideal that I said before. This is for any P and K. These two properties are first order, and the proof that is Euclidean can can be reproduced easily. And I just noticed that in the case of M, M, both standard and non-standard, this is not Euclidean. But when we go to the quotients, this is so. And I give a characterization. The units on this ring can be characterized in the following way: standard way, natural way, where M is prime to P, and so they form they form an ideal, which is the unique maximal ideal. And then you need to internalize the standard approximation that is used to show the Euclideanity and inside M, and this can be easily done. You need to approximate, encode a finite number of divisions. This can be done. So the residue field in this way of M over P to the K M is either FP, if P is standard. I'm not making any distinction for the moment for the P. I'm just in the context of M non-standard. So if P is standard, we have that the residue field is FP. And if P is not standard, then the quotient field is a pseudo-final field because it has characteristic 0 and it's a pseudo-final field. So, so in an Euclidean valued field, what we have to understand, if you can go back to the previous slides, please. So we know about the residue field, and when we are working in an Euclidean local field, because of the work of Ax, Kochen, and Ershoff, what is important to understand is what is the residue field and the value group. And for the case of characteristic 0, both for the field, the starting Euclidean field, and for the residue field, if they are both 0, 0, then we have that the theory of the Euclidean field is determined by the theory of the residue field and the theory of the value group. And this is also the case when the characteristic of the residue field is P, is a prime, and but there is some other condition on the value of on the valuation of P, which has to be the minimum of the group. But this I will come. But just to say that here, what we have to understand is the residue field and of these rings and the value group. So we call truncated ordered abelian groups. We did this analysis with also because they were connected. Direction and McIntyre, they were working on things connected with the adults, and Angus and I were working on in this other context with the residue rings or models of PA. But then we had some common interest on the value group of these two structures. And so we have written a paper together, and we do an analysis of the TOAGs. So what it is if we take an ordered abelian group, which has, we take an ordered abelian group and we take an element, which is tau, which is bigger than 0. And then we truncated that tau, and we induce an ordered abelian group structure on the initial segment 0 tau as the following. We say that we define the addition in terms of the addition on the starting G. When the value, the sum is below tau, is what it is in the big group, and if it is not in tau, then if it is bigger than tau, we truncate it at tau. And we give an axiomatization of the TOAGs, and in the first order language of ordered abelian groups plus tau, which is this last element. So we find these axioms which are true in all TOAG obtained as I described before, starting from an ordered abelian groups, just cutting. And conversely, we show that if we take any model of what is a TOAG of the axioms we identified, then we can construct an ordered abelian group and an element in this group, such that if we do the process of cutting at this element, then we get an isomorphic copy of the TOAG we started with. So we have characterized them in this way. In our context, we need some extra axioms because we are interested in groups. The value group is discrete, and the TOAGs we are interested in come from Pressburger models. So we know that in the analysis of Pressburger arithmetic, we need an extra constant symbol 1 for the minimum positive element, the least positive element. And so we expand the language with this least positive element. And what we have is we define what is a press TOAG. So a TOAG, a group on an initial segment of some group, a TOAG of as before, but which comes from a Pressburger group. This is the idea. And so we characterized, we defined this, that is a TOAG with the least positive is a press TOAG if and only if it satisfies this condition. So it's discretely ordered, and every positive element has a successor. And then we have to say also the division, the congruence conditions that we know on Pressburger, and we have to extend to have for this initial segment. So this is a characterization, and this can be first order axiomatized, have all the notions that are expressed here. So as I said, this is an axiomatization, the slide before, of the TOAG we work with, the press TOAG. And we need also to have in the language a new constant symbol for the top element, because otherwise we may not have the model completeness, because if we take two, if we take two TOAGs, Pressburger TOAGs, and if they have different last element, if the element are not the last, we want the last elements have to have the same type. For this, we need to add the constant to the language. So this is the reason for expanding to TOAG. So every model of a Pressburger TOAG is model complete, but this is not complete. It's not a complete theory because it depends if we don't want to exclude that thinking about the setting we started working with as the residual ring of M over P to the K M, that K can be either a standard element or a non-standard. So we have to specify what if we have an initial segment which is finite, or if it is the right-hand side limit is a non-standard element. So for this, the complete extensions are given by either by if a tau is a natural number, or if it is bigger than all, then this is a fancy way of expressing the congruence condition that tau has to satisfy for all the powers of P to the K. So the Pressburger TOAG plus tau is congruent to as this theory. Then the theory of Pressburger TOAGs has quantifier elimination in the language with the congruence conditions. This is the same as for the theory of Pressburger arithmetic. We know that there is a elimination of quantifiers in this expanded language. So it's a model complete, it's not model complete. Each elementary type is determined by the position of this tau with respect to the standard elements, to natural numbers, because we said that before there is a 1 and then every element has a successor. So we reproduce a copy of n. And then we have to say how the congruence condition for tau work with all the P to the K with respect to the P to the K power. Okay. So, so what have we done until now? We can summarize that if we take this ring M over P to the K M, this is a ring. Okay, what we have is that for any ring like M, our quotient ring, we can find a ring R such that R is an ancillary evaluation domain of characteristic 0, and it's unramified. This is when the characteristic of the residue field is P, and we want that the valuation of P is 1. If the characteristic of the residue field is 0, there is no extra condition. So if R is an ancillary evaluation domain of characteristic 0 and unramified, and the value group of R is a Z group, and we can find this, and then we can prove that the residue ring, our residue ring, starting with a model of Peano arithmetic, is isomorphic to the quotient ring R over I for some principal ideal I. And the residue field of R is naturally isomorphic to the residue field of M of our residue field from arithmetic. So what I want to stress here is that this theorem, and I will give a short proof for this, is an equivalent of what McIntyre had done in the case of k is equal to 1. And also, it makes appearing this, these rings, m over p to the k m, to the m quotiented by p to the k m, in a context which is not related to arithmetic. We have that is the second statement, that this ring is isomorphic to a quotient ring for a ring R, which is an NCD evaluation domain, which has a value group, a certain value group. These are all notions which are not connected to arithmetic. So we can find in nature these quotient rings, and they don't come only from a construction ad hoc in arithmetic. Okay. Yes, done. This is, I want to give an idea how to find the ring R. And we apply something specific for arithmetic. Maybe there are also other proofs, but we like this one that is more of it's appropriate for the setting of arithmetic. Maybe it can be done also in another way, but we like this. So we know that by McDowell and Specker theorem, there is a proper end elementary extension of M, and we call it N. We take a delta, which is above M, is in N above M, and we do the construction we did before. So we take the quotient ring of N over P to the delta N. For what we have proved, this is an Ancelian local ring. And inside, and we take the following delta, capital delta. This is everything which has valuation above all the elements of M. So M is an initial segment of N. So this form is a prime ideal and is not principal in N. And we quotient N over this delta. So what is left over is everything above delta. So all the elements in M keep, they are not squeezed all together in the quotient as the valuation, because in delta we put all the elements which are valuation bigger than all elements of, the valuation of all elements of M. So this is a local Ancelian domain, and the value group is M. So it's a trick to have the model of PA as the value group of another local Ancelian domain. And we can prove that this relation holds. This is easy to prove. It's just algebra. And from this isomorphism, we get that these R, here is a different R, but it's the same. I just made a mistake. It's Carly, but it's the same R. And the residue field from this isomorphism, the residue field of R is the same as the residue field of the quotient ring of arithmetic. And so it's either FP or a characteristic zero pseudo-finite field. So this explains the three properties that I mentioned before, that were stated before. So what we can summarize is the following, that if M is a non-standard model of Peano arithmetic, we have two cases. This follows from Ack's work. that if M is standard, then, and no hypothesis on K, it can be either standard or not, then we can find a ring, the quotient ring of M is isomorphic to a quotient of a ring elementarily equivalent to ZP, the ring of integers, p-adic integers. And if P is not standard, then this is isomorphic. Again, is a quotient ring, but we can say something more about that R because of the characterization due to X. That is, this is elementarily equivalent to a power series ring constructed over a pseudo-finite field of characteristic 0 if P is not standard, and gamma is a Z group. So this is also the, so we try to understand a bit better what these rings are. And then we want to have also converse. We want, if we start from any quotient of a ring S as above, in both cases, 1 and 2, then we want to find a model of PA which is elementarily equivalent to that quotient. So we want to represent any quotient S over alpha S as a quotient of arithmetic, connected to models of arithmetic. And the theorem is this. And we get it like, this has, again, the model of PA that we have, we construct is an ultra product of Z. Yeah, I sketched here the proof. So this is, again, I said that this follows from a result of X quotient and Bischoff. So S is an ultra product of the ZP if it's one of the above cases, in both cases. So it depends on D. If D is a principal ultrafilter, then you have that the S is elementarily equivalent to ZP, which corresponds to P standard, the prime P standard. And if P is not standard, then you have a non-principal ultrafilter. And so, so you have that the quotient S over alpha S for some alpha in ZP is elementarily equivalent to an ultra product. You keep on the ultra product, and because of the property ultra product, you get this isomorphy, this elementarily equivalent. And then we remember that the quotient, it was one of my first slides, the quotient of the p-adic integers, a quotient ring of the p-adic integers is isomorphic to a quotient ring of Z. And then here it is, the model, the non-standard model of PA, which comes out. So the elementary theories of this are exactly the elementary theories of these quotients obtained as described above. And this gives the decidability of the theory of what is known, what was known for Z. This is obtained also for the rings coming from a non-standard model of PA. So this generalizes what is in Ack's paper for Z modulo, the ring Z over P to the K Z. Okay. Yes, this is elementary equivalence, but it's not isomorphism. The same thing as for the case of K equal to 1 in the previous paper of McIntyre for the case where K is equal to 1. Again, if we add some resplendency, this can be the elementary equivalence comes isomorphic, and in case of countable, then we have that recursively gives recursive saturation gives the isomorphism instead of the elementary equivalence, something more. Then here, I mean, I'm not going too much into the details because so we have obtained then also. Can you go back? Sorry. Also one more. Okay, from this we have also that there is a okay, I mentioned this, the decidability of the theory of all m over p to the k m. And then, okay, go back, go forward. Yeah, thanks. And of course, when we do the model theoretic analysis, what we want to find is an elimination quantifiers and also the model completeness. And then we have these two. I mean, it's a bit long to explain, but essentially we have elimination of quantifiers for the theory of all m over p to the km. Any distinction on pk, they vary all over m, and for any model of PA. And this is used for some known language for evaluation theory. And of course, the last two are for dealing with the quantifications over the sort from the group, from the value group, and this other one is for the sort from for the residue field part, for eliminating quantifiers for the residue field part. And then for the model completeness, not always you have that the theory of each one of these rings is model complete. There are some which are model complete, some which are not, and I put some examples here. There should be this. And we characterized those which are model complete. I mean, this is a result like a la Ziegler, that the model completeness of the valued ring is expressed in terms of the model completeness of the residue. This is this little k here is the residue field, and the value group. The value group we mentioned some slides before. That it's model complete. And so for the value group, it's, let's say, it's for free. So the theory, the model theory of the ring, of a ring elementarily equivalent to S over alpha S, which is one of ours, it depends on the model completeness of the residue field. And I want to, I mean, this is just sketchy, just to say, this is, I cannot say too much in details here, but just to give an idea of what is the problem for the general case where n is any element. So n is composite. So it can happen that if n is, we know that in model of PA we can give a meaning to the factorization as it's expressed in the top of the slides. It has a perfect good meaning. We can define the p-adic valuation. We can say what it is, the product. There is all machinery that we can. This is very well known, and so the case is depends if this product, if there are finitely many primes which divides n, or if there are infinitely many primes. So if either S is standard of F, S is not standard. Of course, from the inside of the model, everything is finite, but outside, no. And so the idea is to use, but for the treatment to use a result of Pfefferman and Vogt, which reduces the satisfiability of a formula in a ring, which is a product of rings. I take R, a product of rings. And why this? Because here, if N is the product of, I didn't write it down, but yes, consider here, maybe here is written, yes, better. And I mean, this is not M equal to this. This is missing M over NM, the ring, sorry, in both lines. I hope it's clear. I mean, in M is not this product, but M over N in both 1 and 2. Yes, yes, exactly. Yeah, yeah, thanks. Yeah. The M is M over NN. So in the first case, this is a genuine product of rings, but in the second case, this is not, let's say from outside, a product of rings. We can deal, it seems that it's useful, this a theorem, Pfefferman and Vogt, which gives a necessary sufficient condition for the satisfiability of a formula in a ring, which is a product of rings, and works also for sentences. In terms, it's a transfer to the satisfiability of a formula in the language of Boolean algebras, in the Boolean algebra of the idempotence of the ring. So we switch from rings to Boolean algebras, well, to Boolean rings, working with the idempotence. And so for the case that has a standard is quite, it seems working. For the other case, well, it cannot be applied directly, but you need to have a version of Pfefferman-Vogt from the inside, because inside, of course, inside the model M, this is a finite product. So you need to put yourself inside the model and have a formalization of Pfefferman-Vogt inside the structure M. And this will give, at the end, hopefully that it works, will give that the theory of the quotient M over NM coincide with the theory of the quotient, and since of the quotient rings of Z. And since this one have been proved to have this theory is decidable, we will get that also for M non-standard, this is the case for general M. This is sketchy because we are working on, I mean, this is just some ideas that we are pursuing, but I cannot say more about this further in this direction. It's just some ideas that we are developing. And I have finished.
Okay, thank you very much, Paola. Now we all clap. You can see it or you can hear it. Thank you. And it's time for questions.
I have a question to start. Hello?
Go ahead, go ahead.
Yeah, yeah. At one point early on, you mentioned Bombieri's version of the Weil-Riemann hypothesis for curves.
Yeah.
How far into this analysis does that relevance of that result persist?
I mean, that one, I think I mean, that has been done. There is a formalization of this result in PA.
Yeah, but my question is, how often do you resort to this result as your analysis proceeds?
Oh,
how much depends on it? I mean,
we reduce everything to arcs at the end.
Mm-hmm. Ah, okay.
Yeah.
Thank you.
So how much induction do you really need in these results?
Oh, hi, Dave. I haven't seen you. Well, maybe to code about coding. I don't know. Some can be done, of course, in delta zero plus exp. Yes, I think. Some of the coding you have to do it. You need exp. Well, I haven't thought too much about if it can be done further down. There are many things can be done. I mean, for example, the product can be given a meaning also in models of delta zero for the last slides. Yeah, this product have a meaning also there. Well, we don't know. Yes, I mean, in delta zero, for example, even in delta zero plus omega 1, you don't know that one that was asked about this Bombieri stuff. We don't know. In delta zero plus omega 1, only the first two, that is perfect, and is it has a unique extension of each finite degree.
I see.
That is known. We proved it, but the other one we don't know. We don't know that it's a PAC.
Thanks.
Okay.
You did use the McDowell-Specker theorem early on. Would that be a problem?
No, say again. I didn't understand.
You used the McDowell-Specker theorem, which suggests
okay.
you do need all of PA maybe.
For the weaker, yeah, but I mean, I don't know. There was a referee who claimed that it's not necessary to go to so fancy to do this. We believe that we liked our proof, but because it uses something from arithmetic, a referee didn't said was not necessary at all. We still have to understand the proof that he or she had in mind. For us, this works. I mean, there is no attempt to go down further. We haven't thought yet. Well, as Dave asked, of course, we thought when if it is the same characterization that Angus had for k equal to 1, it works also for models of I delta 0 or I delta 0 plus omega 1, but we know only that the first two for I delta 0 plus omega 1. And this one, yeah, I mean, I don't know if the referee proposes what is proposed, then if it can be so general, maybe more algebraic could be done, but I mean, I don't know. I haven't checked what was suggested yet.
Well, perhaps for this result, you don't need a full elementarity, maybe just an end extension with enough elementarity is enough.
Because maybe you want, where is it?
You just need something non-standard with respect to M.
Non-standard. Yeah. Maybe. For I delta 0, there is an end extension, yeah. Yeah, it can be done. I don't know if we need later in the proof exactly. Maybe some elementary stuff, some. No, it seems no, we don't. Yeah, maybe it could be done only with end extension, not elementary. Could be maybe.
Okay. More questions? So, since I don't hear any, so let's thank Paola again. Thank you very much. Great talk.
Thank you.
Somebody commented somewhere that, you know, this is fantastic that we'll keep going through the East, you know, the spring break. I didn't even know that there was a spring break. So
Yes.